Hello friends, welcome you in my YouTube channel. I am Dr. Mohammad Sirajul Faizi. Today in this video I am going to talk about pericyclic reactions. So I will talk in this flow: introductions, then classification, then I will talk about mechanisms, and then examples. So pericyclic reactions are any concerted reaction in which bonds are formed or broken in a cyclic transition state. Electrons move around in a circle. That is, there is a single transition state from start to finish, in contrast to a stepwise reactions. So, energy versus reaction coordinate. This is starting materials, and this is the product, and this is the transition states. In multiple reactions, transition states, starting material, intermediate, again intermediate, and products. So pericyclic reaction is a concerted. Pericyclic reactivity can be understood in terms of frontier molecular orbitals theory, and the outcome of reactions can be predicted using the Woodward-Hoffman rules. Pericyclic reactions require light or heat and are completely stereospecific. That is, a single stereoisomers of the reactant forms a single stereoisomers of the product. Properties of pericyclic reactions: little if any solvent effect, no nucleophilic or electrophiles involved, not generally catalyzed by Lewis acid, highly stereospecific, often photochemically promoted. Now, classifications. In this slide I will talk about classification of pericyclic reactions. First one is cycloaddition reaction. Second one, electrocyclic ring closing and ring opening reactions. Third one, Sigmatropic rearrangements. Fourth, Cheletropic. And fifth group, transfer reactions. Now I will discuss about cycloaddition reactions. A cycloaddition is a pericyclic chemical reaction in which two or more unsaturated molecules or parts of the same molecule combine with the formations of a cyclic product in which there is a net reduction of bond multiplicity. The resulting reaction is a cyclization reaction designated as A plus B. A and B refers to number of atoms containing pi electrons. Three important classes of cycloaddition reactions: Diels-Alder reactions, 2 plus 2 cycloadditions, and 1,3 dipolar cycloaddition. In this slide I will talk about Diels-Alder reactions. Discovered by Professor Otto Diels and his student Kurt Elder in 1928 and received Nobel Prize in 1915. Reactions between a conjugated diene and dienophile. Highly effective method for the formations of cyclohexane ring. You see, this is diene and dienophile forming cyclohexane. Diene must be in the S-cis conformations. This will react, but this not. So dienophile with electron withdrawing group react faster. This is because the electron withdrawing groups reduces the LUMO energy and improves the overlap with the orbitals in the die. Now look at the examples here. The reaction is stereospecific and end product often favored. In a kinetically controlled product is faster to form irreversible. The endo is favored, but for reversible reactions, thermodynamic favored or control, the exo may dominate with figure. Now, HOMO approach. Cycloaddition can be explained using frontier molecular orbital theory. Frontier molecular orbital theory was developed in 1960 by Kenichi Fukui, who recognized that chemical reactivity can often be explained in terms of interacting highest molecular orbitals, HOMO, lowest unoccupied molecular orbitals, LUMO. The alkene dienophile component has 2 electrons in a single pi bond. HOMO theory here identifies the HOMO and LUMO components of this system. Highest occupied molecular orbital psi1 and lowest unoccupied molecular orbitals psi2. Likewise, the diene, which has 4 electrons in its conjugated pi system, can have its HOMO and LUMO identified within frontier molecular orbital theory. So psi1 here, psi2, psi3, psi4. Psi2 is HOMO and psi3 is LUMO. Now, if you examine the phases at the ends, terminus of diene and dienophile, we find that the LUMO-HOMO interaction are phase matched. So LUMO is psi2 and HOMO is psi2 in alkene. So this is matching. Or this form and this form is matched. In the HOMO diagram above, the size or coefficients are all the same size, but usually they are different sizes. The rule is that the coefficient match as well, a small with a small and large with large. Thus, the reactivity of the cycloadditions can be explained. 2+2 cycloaddition reactions. The 2+2 photocycloaddition is a cycloaddition type reaction. It generally entails the formation of new molecules by reactions of 2 unsaturated molecules via 2 atoms from each molecule, hence 2+2. So look at the molecule under light forming singlet, singlet converted into triplet, triplet converted into triplet excipients, and triplet diradicals, and singlet diradicals, and then cycloaddition. 1,3 dipolar cycloaddition reactions. These are 3 atom 4 electrons diene with react with dienophile and form 5-member ring. 3 atom and 4 electrons. This is called 1,3 dipolar, and this cycloaddition reaction called as 1,3 dipolar cycloaddition reaction. What is the mechanism shown here. Now, sigmatropic rearrangements. Molecular rearrangement in which a sigma bonded atoms or group flanked by 2 or more pi electron system shift to a new location with a corresponding recognitions of the pi bonds are called sigmatropic reactions. The total number of sigma bonds and pi bonds remain unchanged. Different types of sigmatropic rearrangement reactions are 3,3 sigmatropic rearrangement, 2,3 sigmatropic rearrangement, and 1,5 sigmatropic rearrangements. Halogen rearrangement are 3,3 sigmatropic rearrangements. Look at this example. It undergo heat and forming this product. This is example of 3,3 sigmatropic rearrangement. This is one-step mechanism without ionic intermediate or any charge, similar like a cycloaddition reaction. Now, electrocyclic reactions. An electrocyclic reaction is a reversible reaction that involves ring closure of a conjugated polyene to cycloalkene or ring opening of a cycloalkene to conjugated polyene. For example, ring closure of 1,3,5-hexatriene forms 1,3-cyclodiene, a product with one more bonds and one fewer bonds than the reactant. Ring opening of cyclobutene forms 1,3-butadiene, a product with one fewer bond and one more bond than the reactant. So look at this example, ring closing reaction 1,3,5-hexatriene. It is favored by heat and forming 1,3-cyclohexadiene. So triene become diene. Ring opening reactions here, cyclobutene undergo forming 1,3-butadiene. So ene become diene. Example of pericyclic reactions: synthesis of citral, Fischer-Indol synthesis, pericyclic reaction in biological system, oxidation of 3-alcohol to carbonyl compound, synthesis of substituted alcohol, Diels-Alder reactions, alkaloid synthesis, synthesis of intermediate of esterone, Diels-Alder reaction for synthesis of carbohydrate. So friends, thank you. Hope this video will be useful to you. If you like this video, then subscribe my channel, and thanks for watching.